All right, good afternoon. As you said, I'm Mike Fox. I'm in the ZOS Communication Server Design Group. I've been working on routing on ZOS since about the mid-1990s when I started working on the OMPROUTE daemon. I was involved in the efforts to add IPv6 and several new functions to that as well. I'm in the design area, and routing is one of my portfolios. So let's go ahead and get started because it is a long presentation. We cover a lot, and even though we cover a lot, we don't cover anything really deeply because there is so much to cover. So looking at the agenda, you can see we have quite a bit to do. We'll start off just by reviewing some basic IP routing concepts. Then we'll extend that to how they apply to ZOS. Then we'll talk about dynamic routing, first with concepts, and then with some specific OMPROUTE implementation discussions. Now, originally I was asked to do a presentation on OMPROUTE, but I think IP routing is a broader topic, and without the context of the IP routing, the OMPROUTE stuff doesn't make a lot of sense. If after we get through with this, people think we need a deeper dive on OMPROUTE, we can consider doing that in a future presentation. But this is mainly about IP routing, with OMPROUTE as one of the parts of it. So let's start on slide 4 with some basic IP routing concepts and just talk about how IPv4 addresses are constructed. And this matters because classes do matter in routing. So you've probably seen this before. These are the classes of IPv4 addresses. The class of an address is determined by its first bits. Whereas, bit 0 is class A, and then 10 is class B, and 110 is class C. And what the class do is divide how much of the IP address is the network and how much of it is a host ID. And you can see with these classes, they're generally divided on an octet boundary. So you have a mask, which is shown there, for example, 255.255.255.0. The mask covers the part that's the network part, and then the rest is the host part. It's also expressed as a number of masked bits because it's kind of awkward to write and say 255 so many times. So, for example, a /24 means the first 24 bits are the network ID, and then the meaning last 8 bits are the host ID. Now, there's the concept of a class mask, which is simply the network mask that goes with an address class. So, for a class A address, the class mask is 255.0.0 or .0 or /8. Class B has a /16, and class C has a /24. And those are the basic addressing classes and subnet network divisions. Now on page 5, a network address, there's several different levels of addressing. Starting off with the network address. With the network address, that just means the mask is equal to the class mask. For example, 9.0.0.0/8 is a network address because it's a class A network and it's got the same mask as the class mask. Then there's the concept of a subnet address, which means the mask is longer than the class mask, so the standard host portion has been subnetted. For example, 9.1.1.0/24 is a subnet because the network is the 9 network, but we've added 2 more bytes of the address and made a subnet. And then there's the concept of a supernet address. With a supernet address, the mask is shorter than the class mask, so you've got multiple networks being addressed by one address. For example, 192.168.0.0/16. Well, 192 is a class C address, so it should be 3 octets of address of network, but we're only using 2 of them. So we've grouped a bunch of networks together. Then within an address, you have the host address. With a host address, that means the subnet mask is all ones, or 255.255.255.255, or /32. A host mask addresses a single host on the network. Now the reason we're discussing this is because networks, subnets, and supernets are key to IPv4 routing. They allow you to collapse multiple addresses into one addressable entity, so you reduce the number of routes. For example, you can do a route to a network, like a route to 9.0.0.0/8 is a network route, and it reaches every IP address in the 9.0.0 network instead of having to have a zillion host addresses to reach every host in the network. Similarly for subnets and supernets. So going on in slide 6, we have this concept of classless interdomain routing, or CIDR. Classless interdomain routing is just a fancy way of saying we don't really care that much about networks. Everything is a subnet mask. And that's how modern networks are implemented. Almost everybody uses CIDR. CIDR just means that the subnet can be any arbitrary length that the network administrator sets it to be. Usually you have one subnet per LAN segment, and then you can group together multiple ones into a network. Now, within a subnet, there are 2 special reserved addresses. There's the subnet broadcast address. With the subnet broadcast address, all the host bits are 1s. Then there's the subnet number, which just addresses the entire subnet. In the subnet number, all host bits are 0s. For example, if you have 192.168.255.255, that's the broadcast address for the 192.168/24 subnet because all the host bits are 1s. And then 192.168.0.0 is a subnet number for that subnet. these addresses are not available to be assigned to hosts. So what that means is, in reality, the longest practical subnet mask is /30. Even though there's 32 bits in the mask, you can't have a /31 simply because there's not enough addresses. You have to have a subnet number, you have to have a broadcast address, and you still have to have room for hosts. So with the smallest subnet possible, you have a subnet number, a broadcast address, and 2 hosts, which is what you get with the class 30 network. And that's shown on the example on the bottom of the page. If you break out the binary, you'll see that for the .4 address, the host portion is all zeros, and for the .7 address, the host portion is all ones. Now that's IPv4. Also coming along is IPv6, which is becoming more and more common, and IPv6 is the next evolution of IP addressing. The main difference between IPv4 and IPv6 is the address size. IPv4 addresses are 32 bits long, IPv6 addresses are 128 bits long. Because they're so long, they're written as hexadecimal half words, to try to make the notation somewhat compact. And you have hexadecimal half words separated by colons. And then as a further optimization, multiple half words of zeros can be omitted and replaced with colon. So colon means fill in the space with enough zeros to make this 128 bits. So in the example there, I have an IPv6 address which has 2 half words of colons in the middle, 2 half words of zeros in the middle. Those are replaced by a colon in the second example. Those are the same IP address, and the second notation is the standard one. So there's another important difference, is that in IPv4, an IP address usually has a single, an IP interface usually has a single IP address. In IPv6, IP interfaces can have multiple IP addresses, and they usually do. They almost always have at least 2, which I'll get into in a minute. So we just discussed subnetting and networking. In IPv6, that concept really doesn't really make much difference. In IPv6, instead of using subnets, we use prefix links. There are no address classes, and prefix links are always considered variable. But ironically, even though they're always considered variable, in reality, they're almost always 64 bits. So half of the address is the network and half of the address is the host in IPv6. The prefix notation is always significant bits. It would drive you nuts to write enough 255s to write a mask for an address that long, so we always use the significant bits. For example, the picture here, we have an address that ends with /64. That means it's a 64-bit prefix. And then the next address on slide 8 is what a host address looks like, which is simply prefix length of 128. Because once again, that's saying that all the bits are significant. So, like IPv4, a prefix route addresses all addresses that fall within the prefix. But unlike IPv4, there's no broadcast address, so all the ones addresses are available to be assigned to a host. This is because there is no broadcast in IPv6, only a multicast. So let's go on to page 9, talk about IPv6 scopes briefly. IPv4, all IP addresses are supposedly global, even though a lot of people have used private addressing behind NATs and firewalls and things like that. But officially, in the architecture, all IPv4 addresses are global. And IPv6 addresses have scope, which means an IP address is only unique within its scope. And there's really only 2 scopes that matter. When they first defined IPv6, there were other scopes, but they've been deprecated. There's link local scope, and a link local address is any address that starts with FOXEZ80 with a prefix length of 10, and they are only unique on a specific link. And every IP address, every interface that's not a VIPA must have a link local address, because in reality, link local addresses are how at the link level interfaces are addressed in IPv6. Then everything else is a global address. And the prefix of global address is 2000/3, so just the first few bits. Global addresses can be addressed from anywhere. They have to be unique. And if you do some quick math, you'll find out the IPv6 global address space is huge. I think we've said in the past that there's enough IPv6 addresses available that every atom on Earth can have 2 addresses, so we don't think we'll run out of that anytime soon. Now usually a physical interface has both a global and a link local address, and a VIPA only has a global address. And if you don't know what VIPAs are, we will discuss that coming up. All right, so slide 10 just gives you an illustration of link local scope. I have a picture of 2 networks connected by a router. You'll notice the router has 2 addresses that have the same link local that has 2 interfaces that have the same link local address. You've got FOXEZ8012 on both sides of the router, and that's legal because that address is only required to be unique within the specific link. And it's the only FOXEZ8012 on link 1 and the only FOXEZ8012 on link 12, so that's legal. However, in the lower right-hand corner, we have FOXEZ801234. We have 2 of those on link 2. That is not legal because within the scope of the link, IPv6 link local addresses have to be unique. So slide 11, going back to IPv4, we're starting to get more into a little bit more routing type of stuff, is the address resolution protocol, which is a relatively basic protocol that's used to map an IPv4 address to the MAC address of an adapter. And it really is the most basic form of routing, and it underlies all other routing in IPv4. And at its most basic level, when a stack has an IP address that it needs to send a packet to, it queries everybody in the LAN to say who owns this IP address, and the owner responds and says, I own it, and here's the MAC address. And then when the owner gets the response, he puts it in the cache. I mean, when the sender gets a response, he puts it in an ARP cache, so you don't have to ask every time. So that's relatively basic routing, and that's how it starts off. On slide 12, we have the concept of a gratuitous ARP, which makes ARP more efficient. Now, obviously, it wouldn't be very efficient if a host had to send an ARP request every time he had a packet to forward for the first time. So in general, when a host brings up an interface with an IP address, he sends what's called a gratuitous ARP, which is just an ARP packet that's sent to everybody else on the LAN to a broadcast address saying, hey, everybody, I own 9.1.1.1, and here's the MAC address. And everybody caches that. And then for the future, when other hosts need to send to 9.1.1.1, they already have the MAC address cached, and they can go in and forward it to the correct adapter. There are other things in MAC where obviously these ARP entries can time out. Also, if a host forwards to an ARP address and it doesn't work, he can redo the ARP. So it's a relatively basic protocol for forwarding within a single link. Slide 13, IPv6 doesn't use address resolution protocol, it uses neighbor discovery. However, neighbor discovery is not that much different from ARP, it's just the IPv6 version. It uses ICMP packets, and it has more proactive notifications, and it has more robustness. And it supports some advanced IPv6 functions I'll get into in a minute, like auto configuration of IP addresses. Instead of an ARP cache, there's a neighbor discovery cache in IPv6. But the concepts are very similar, even if the implementation is a little different. So slide 14, getting back to IPv6, another concept that affects routing is stateless autoconfiguration. IPv6 has a feature to allow interfaces to configure their own IP addresses so you don't have to code them, and they're not tied to a specific LAN. So an IPv6 address can be automatically assigned to an interface of IPv6. And the way that's done is, and this is why 64-bit prefixes are commonly used in IPv6. To use auto configuration, you have a 64-bit link prefix, which is owned by the router that controls the link. Then you have the 64-bit interface ID, which is controlled by the local host. You put those two together to generate automatically configured IPv6 addresses. Now, the link prefix is learned from the router as part of neighbor discovery, and the interface ID can be configured on the host, or it can be automatically derived from the link's MAC address. And then there's always a link local address, which is always created because the link local prefix is always FOXeasy80. So you add that to the interface ID, you have the link local address for an interface. Then you take the link prefix that's learned from the router, or it can be configured and add that to the link address, and you have the global address for the interface. So the main advantage of IPv6 stateless auto configuration is that if a host moves, it simply learns the prefix of its new link and automatically reconfigures its interface IP addresses. This is great for mobile devices or any other host relocation scenario. It also allows the router to better control addressing on the link because the router tells you what the prefix is and you use that to configure your IP addresses. Slide 15 shows a very basic picture of how stateless auto configuration works. I have a router on the right, I have a host on the left. When the host first comes up, all he knows is the MAC address of his interface. He sends out a router solicitation, which is a multicast message to a multicast group that routers listen to, basically saying, I'm new here, somebody tell me the configuration. And the router on the link receives that message and responds and tells the host, this is the link prefix and this is the link local address of the default router. So with those two pieces of information, the host can configure its IP addresses. It can create the global address by adding that prefix to the link ID. And it also knows who the default router is, so it can start routing to that router without having to run any kind of routing daemon or any kind of configuration. So in a basic configuration, IPv6 does a lot of this stuff automatically for you. Works really nice. Okay, so let's go on to the next section, starting on slide 16, which is just a discussion of basic ZOS routing concepts, how these things relate to ZOS. So we're going to get more ZOS specific as we go. So slide 17, the basic building block of routing in ZOS is obviously the routing table. COM server TCP/IP has its own routing table, which you can display using netstat route. Netstat route is the console command. There's also netstat, I think, -r in ZOS Unix. And like all netstat commands, you can access it from different methods. And the routing table simply has a list of destinations and which gateway you use to reach that destination and which interface you go out. So for example, for route 3, it's telling you to reach 9.67.115.69. And that's a host route because it's got the /32 prefix. Go out OSA QDIO link and forward to router 9.67.115.72. Now you can also see at the top there's a default route possible, which basically says if the route is not If the destination is not in the routing table, then use this gateway. And then there's a direct route, which is route number 4, which has no forwarding address because that means that the destination is directly on the same LAN that we're attached to. So the number 4 says forwarded out OSA QDIO link, and 9.67.112.0 is directly attached. Since it's a subnet route, that most likely means that 9.67.112.0 is the subnet of OSA QDIO link. Now the method that ZOS uses, and I think all TCP/IP hosts use, is what's called the most specific match route. So you see some of these routes are subnet routes, some of these routes are host routes. So I'm going to switch back and forth a little bit. You go to slide 18, I got an example of some routes being matched. For example, if it looks up 9.67.115.69, route 3 in the routing table is an exact route. That's the best match. That's the route that will be used. If you try to route to 9.67.115.32, there is no host route for that, but there is a subnet route for 9.67.115.0 subnet/24. That destination address falls into that subnet, so route 2 is selected because it's the most specific subnet route available. Next one we're going to look at is 9.1.1.1. You go back to slide 17, you can see there are no 9.1 subnet routes, but there is a default route. The default route is the most specific route available, so it is chosen to route to 9.1.1.1. And finally, 9.67.112.1 is another destination we're going to route to. There is no host route for that, but there is a subnet route for 9.67.112.0. That route will be selected to route to that destination. So that's the most specific subnet route, the most specific match method of picking a route. It's basically how the routing table works in ZOS. Now, on slide 19, there are also flags on the route, and the flags just give some information about the routes, and we'll talk more about these later. The most basic flag, U, means the route is up and available for use, and that flag would not be on, for example, if the interface it used was down. Static routes are coded in the TCP/IP profile, and their flag is either S or Z. And then dynamic routes are learned from OMPROUTE, and their flag is either O, R, or C, depending upon how OMPROUTE learned it, and we'll discuss that more later. A G flag means the host uses a gateway. The H flag means it's a host route, and there's more flags that are documented in IP system administration commands, but these are the main ones. There's also a ref count field that tells you how many connections are currently using the route. So from this NetStat routing table, you can get some pretty good basic information. Now on slide 20, there's also the concept of multipath. You can have multiple routes to the same destination in your routing table. This is called multipath. Those routes will be in the table if they're available, but how they're used depends on how you configure the TCP/IP stack. There's an ipconfig multipath configuration. If you configure multipath none, then the first matching route is always used. So if you configure multipath 1, then the third route in that routing table will be used to route to that destination every time. Multipath per connection, which is what we recommend, means that each connection is assigned to a route in a round-robin fashion. That means for TCP, we assign the connection to one of the routes, and all packets in that connection use that route. For UDP, even though UDP is connectionless, we kind of make up a connection under the covers based on the destination address and the ports, and assign everything going there to that route too. And then there's per packet. And per packet seems like it would be most efficient, but it's really not, and we don't recommend it, because the problem with per packet is if you're sending multiple packets for the same connection over different interfaces, they're likely to get out of order and cause reordering problems, and reordering at the destination is going to cut back your efficiency. So in slide 21, I've talked a lot about IPv4. I'm not going to talk a lot about IPv6 in this presentation, simply because IPv6 routes and IPv6 addresses are kind of ugly to write, and they don't make very good slides. So wherever the concepts of IPv4 and IPv6 are the same or similar, I'll show things using IPv4. But be aware there's also an IPv6 section of the routing table, which the display of that you can see below is not quite as slide friendly. So we'll use IPv4 for most examples and just talk about how IPv6 might be different, or what IPv6 might do. All right, so slide 22, we'll start talking about route types. The most basic route type is a static route. A static route is defined in the TCP/IP profile. It is not learned from the network. So when you define a static route in the TCP/IP profile, there are two types of static routes, and I think this might be relatively unique to ZOS. There is a replaceable static route, and what that means is if you code a static route and you indicate it's replaceable, then OMPROUTE can still learn a dynamic route from the network and replace that route. Then if the dynamic route disappears or is lost, the replaceable static route is restored. Which means the best way to think about replaceable static routes is their last resort backup routes to be used when dynamic routing fails to find a destination, because dynamic routing will always override them, but they'll be available if there's no dynamic route. Netstat, the route flag for a replaceable static route is Z. So if you see a Z in the netstat flags, it means it was coded as a replaceable static route. The other kind of static route is non-replaceable. And what that means is it's coded, it cannot be dynamically learned. So you must use a static route. If you code a static route that's not replaceable, it must be learned. A new route will not be learned dynamically, or if it is, it won't be used. But that has a drawback. If the non-replaceable route is unavailable, for example, it uses a router or interface that is down, and you have dynamic routing and it learns a route that is available, too bad. You made this route non-replaceable, it will be used, so you'll make the destination unreachable. The netstat flag for these routes is S for static. Now, static routes are easier and simpler because you don't have to run a routing daemon, you just have to code them in the TCP/IP profile, but they do not provide any automatic rerouting around failures, and they don't provide any rerouting around network changes, simply because if the network topology changes, you have to reconfigure the static routing table manually. Slide 23 shows how static routes are defined in the TCP/IP profile. We use what's called the begin routes block. It starts with the begin routes, end with end routes, and there are routes inside, in between it. You have a route statement to define each route. I might have to look, I think I might have a mistake here. I think it needs, the default routes, it needs to be route default. I don't remember if the route keyword is required on default routes or not. But in this table, you give the destination, the first hop, the link name, the packet size, and any other options. Now, the reason the packet size is important is because that will override the interface packet size. Any sends that use that route out of the routing table will use the packet size specified. So, for example, if OSA QDIO LN1 actually supports jumbo frames, but the default route has an MTU size of 2000, that's the MTU size we'll use on the route regardless of the underlying hardware. So the MTU size on the route is kind of the final determiner. Now, the MTU size on the route in some cases can be learned from the interface, but if you code it, it's going to be used. Also, I'll draw your attention to some of the first hops are equal signs. That means that it's a direct route, no next hop necessary, so that's equivalent to the 0.0.0.0 next hop in the routing table. And also, if you look under the options slide for the fifth route coded, REPL is how you indicate a route is replaceable. So a static route is considered to be non-replaceable unless you code it otherwise. Also, IPv6 routes are defined right alongside IPv4 routes in the same routing table using IPv6 addresses. It's one begin routes block for both IPv4 and IPv6, and all routes are defined in one begin routes block. So on slide 24, it reemphasizes the point that if you're going to modify static routes, you have to code a new begin route and add it to the TCP/IP profile using variobey. And just as a review, variobey files the command that applies changes to the TCP/IP profile. You have to code a whole new begin routes block because the new begin routes block is a complete replacement. So when you variobey in a new begin routes block, all the static routes are deleted and then they're rebuilt from the new table. Now, you're also only allowed to have one begin routes block. If you have more than one begin routes block in a profile, the last one replaces any previous ones, and the single block contains both IPv4 and IPv6 routes. So, for example, if you have a begin routes block with a bunch of IPv4 routes and you want to add an IPv6 route, you have to recode the entire routing table, including all the IPv4 routes, and variobey it in. If you variobeyed it in with just one IPv6 route, you would wipe out all the IPv4 static routes. So that's how you modify them. You see it's not quite as handy as dynamic routes, even though it's simpler. So slide 25, you might ask, why use static routes? Because they have so many limits. Well, mainly, they're simple. Right? Static routing is most useful in a simple, stable configuration. Not a lot of topology changes, not a lot of things failing. For example, if ZOS is not in a sysplex and is on a LAN with a router that takes responsibility for all routing, then you might just have to have a routing table that consists only of a default static route that points to the router and a static subnet route for the attached LAN, and that may be sufficient. So that's basically saying, I'm on this LAN with this router, I'm pointing a default route at him, he's responsible for everything. But remember, routing goes two ways. Hosts and the network still have to be able to reach back to you. So if you're not using dynamic routing, you're not advertising your destinations, which means if you just have a static route pointing to the router is going to have static routes pointing back to you. Because when you send a packet out, the replies have to be routed back as well. You have to remember the routing is two ways. It's a common mistake that people forget when they're debugging routing problems. They say, I have a route to the destination, but what they don't check is, does the destination have a route to come back? If you're using a flat layer 2 network, though, that's ameliorated, and I'll talk about that in a minute. So a static route configuration is simpler and uses less CPU, but with limited resilience. In the example above, if you were on a LAN with a router, then you had a default route to the router, trusting him to take care of everything. If that router goes down and the backup router takes over, you have to reconfigure your static routing table. So on slide 26, I mentioned VIPA a couple times. I don't know, I also introduced it when I did the basics of comp server, but let me just give a quick review of what a VIPA is. VIPA stands for Virtual IP Address, and it's an IP address that's not tied to a specific physical interface. A VIPA represents something else, any higher level concept. It can represent a host, it can represent an application, it can represent a load balancer. For example, in the picture here, on the ZOS host, I have KIX Apple A, which is represented by VIPA number 2. So VIPA number 2 is the IP address of that KIX application. The client down at the bottom asks to connect to the KIX application, and the name server returns VIPA 2. So the client routes to VIPA 2. It doesn't care where VIPA 2 is. VIPA 2 could move to another host, and also the 3 OSAs along the bottom, 1 or 2 of them could go down, but you can still reach the VIPA because you aren't using an interface IP address on the stack to reach it. Most ZOS IP hosts have a VIPA that represents the entire host, and most applications and sysplexes have VIPAs that represent their own concepts so that the VIPAs can move and routing can automatically discover the new destination, and also specific physical interfaces can go down or even be renumbered, but the VIPA IP addresses don't change. So it improves convenience and resilience of routing. And the key point of a VIPA is it's not tied to a specific physical interface. It just represents a concept. And you route to it through the physical interfaces on the host where the VIPA is living. So that given on 27, let's talk about what a flat layer 2 network is. So a flat layer 2 configuration means everybody's in the same subnet, including the VIPAs. With a flat layer 2 subnet, if you have virtual IP addresses on a host, they need to be in the same subnet as the attached network for it to be called flat. So the main disadvantage of this is that limits VIPA flexibility. You're saying the VIPA has to be in the same subnet as the LAN, and it also means the VIPAs are tied to a specific LAN. They still get the resilience advantage of having multiple IP interfaces on the same LAN serving them, but they can't be served by multiple LANs. But the advantage is, if you're doing static routing only, a flat network improves robustness. So as a really high-level review, if you're using dynamic routing, VIPAs can be in any subnet. If you're using static routing, you want VIPAs to be in the same subnet as the attached LAN. And I'll talk about how that works in a minute. So the reason a flat layer 2 network is powerful is because ZOS Communication Server and OSA together communicate. And ZOS Communication Server registers all VIPAs that are in the same subnet to an OSA interface to that OSA interface. So I'll show that on a slide if that is confusing. But what that means is the OSA performs ARP on behalf of the registered VIPAs, and it forwards packets to registered VIPAs to the TCP/IP stack. And this is a unique ZOS+OSA value-added function. Now if this is confusing, let's go to the next slide where we have a picture. So slide 28 shows a configuration where we have a flat layer 2 network. We have an IPv4 subnet whose subnet address is 10.1.1.0. It's a 24-bit subnet, so the first 3 octets are the subnet, and the last octet is the host. If you look at the configuration here, I have a VIPA on TCP/IP that's 10.1.1.10. So this VIPA is in the same subnet as the OSAs. You can see the OSA addresses are all in the 10.1.1.0 subnet. Now on TCP/IP I have a VIPA as well, but it's not in the same subnet. So TCP/IP is not a flat configuration. TCP/IP is a flat configuration. And what are the advantages of this? Well, if we animate a little bit, what happens is the stack on the left registers to the OSA that VIPA 10.1.1.10 is on this host. And so the VIPA says, okay, I'll pretend that IP address is on me. So that OSA will do a gratuitous ARP. The OSA on the left will do a gratuitous ARP, and it will also respond to ARP requests for its own IP address, 10.1.1.1, as well as the VIPA, because the VIPA is in the same subnet. So if you look at OSA A's address table, he knows that he's the ARP owner for 10.1.1.1 and the ARP owner for 10.1.1.2. 10.1.1.10. 10.1.1.2 is on the other OSA, so he's not responsible for that. And 10.1.3.1 is not in the same subnet because it's an XCF IP address, so he doesn't ARP for that. That means that if the router ARPs for the VIPA address 10.1.1.10, then the OSA on the left will respond and say, it's here, and the packets will get forwarded. So in that way, you get some routing to VIPAs without running a dynamic routing daemon. Now, I've got ahead of myself there. The router's ARP cache then shows that 10.1.1.0 lives on MAC 1. So as far as he knows, it's on the OSA. So this is a pretty nice feature of ZOS combined with OSA, this kind of ARPing, but it also gives some other advantages that may not be apparent. But the key is that the VIPAs have to be in the same subnet as the OSAs. On the right, the VIPA is in subnet 10.1.2, It's not in the same subnet as the OSA, so it's not eligible for this optimization. So if we go to slide 29, we'll see how this optimization gives you some resilience. So on slide 29, we're back where we started, where we have 10.1.1.10. That VIPA is in the same subnet as the OSAs. So OSA A is the VIPA owner. He's responding to ARPs for 10.1.1.10, and the router thinks that 10.1.1.10 is on MAC 1, which is OSA 1, so we are getting to the OSAs. But now let's move the OSA. Let's move the VIPA. So now we move VIPA 10.1.1.10 to another LPAR. And this is not that uncommon with VIPAs, especially in sysplexes. They can move around. It's an availability feature. When that happens, then OSA port C on the other host becomes the VIPA owner, and he sends a gratuitous ARP to the network telling them, hey, 10.1.1.10 is on me now. That causes the router to replace the ARP entry from MAC 1 to MAC 3. So now when the router gets a request to go to 10.1.1.10, he will forward it to the OSA that's port C. So you see there, even though we're not running a dynamic routing daemon, we're only doing flat layer 2 routing, we're able to have a certain amount of resilience and network changes because of the way OSA and TCP/IP cooperate. And that is why there are a lot of configurations we find that dynamic routing isn't really necessary. If you can have a flat layer 2 network, then you can avoid dynamic routing on ZOS altogether. So there's even more layer 2 resilience that we provide, which is called ARP Takeover. And we're on slide 30 now. So ARP Takeover is an additional function for resilience. And what happens here is when a ZOS TCP/IP stack has multiple OSA interfaces on the same subnet, and remember the same subnet also means the same VLAN, the same LAN segment, the interfaces learn about each other. They send out pings, special pings, they learn about each other, and they form a LAN group. So the two OSAs say, hey, we're on this LAN together. And they back each other up seamlessly. If one of the OSAs goes down or fails, the other OSA starts ARPing for its IP addresses. So basically all the IP addresses on the failed OSA get taken over by the OSA that went down. Then when the OSA comes back, it takes them back over. So what you get there is seamless failover between OSA interfaces in case of failures. That might be a little bit complex for words, so in slide 31 we've illustrated it. Slide 31 we have a single host. It's the same as before. We have a VIPA that's in the same subnet as the OSAs. We have port A and port B. Port A is 10.1.1.1. Port B is 10.1.1.2. And port A says I own the IP address 10.1.1.1 and I own the address 10.1.1.10 because it's a VIPA that was registered to me by the stack. I don't own 10.1.1.2 because that's the other OSA. OSA port B says I only own 10.1.1.2 and the other OSA owns 10.1.1.1 and 10.1.1.10. Now, if the OSA on the left, port A, fails, what happens is the OSA on the right takes over those IP addresses. So port A, he loses his table, he's gone, and port B becomes the ARP owner for all the IP addresses, 1.1.1.1, 1.1.10, plus 1.1.2, which are already owned. It sends out a gratuitous ARP and tells the router, hey, these IP addresses that were on MAC 1 are now on MAC 2. So in that manner, OSA 2 has seamlessly taken over the responsibility of OSA 1 in the case of a failure or takedown of OSA 1. And once again, it all happened using flat layer 2 routing with no dynamic routing. So on slide 32, how do you know this is happening? We have some monitoring capabilities. When an OSA goes down and another one takes over his ARPs, a message will be put out saying OSA QDIO2 is taking over ARP responsibility for OSA QDIO1. Then when OSA QDIO1 comes back, you get another message indicating that OSA QDIO1 has taken back his ARP responsibilities. Also, netstat devlink will track the state. If you look at netstat devlink, it displays ARP information and neighbor discovery information. It also lists the LAN groups. So it shows you, for example, LAN group 0010 has only one OSA in it, so he owns the VIPA. That's not much of a group. But LAN group 00001 has two OSAs in it, and EZ60SM02 is the VIPA owner, which means the VIPAs in the same subnet are responded to by that OSA. So there's some pretty powerful capabilities there. If networks can be designed to be flat, you can eliminate a lot of the need for dynamic routing on ZOS. Now there's a bunch of fine print I'm not going to read here, but basically what it boils down to, if you're going to do this, your layer 2 network better be reliable, right? Because you're relying on the routers you're relying on at least one OSA being up, you're relying on the router fabric and the switch fabric to be good, but also the key of a flat layer 2 network is it ties everything to one subnet. So if you're attached to two different subnets, OSAs can only be recovered from the subnet that they're in the same subnet as. So in the previous pictures, if there had been like a 10.7 network, you wouldn't be able to recover that one. In a flat layer 2 network, you have to recover to the same subnet. Everything happens within the subnet. So it does have some limiting. All right, so that's static routing and our flat layer 2 networking. All right, well, let's go on now and start getting into some more dynamic routing concepts, starting on slide 34. So in slide 35, there are 3 dynamic routing protocols that ZOS supports. Well, actually, it's really 2.5 because one of them is kind of trivial. So the first dynamic routing protocol is what we call connection routing, and that's relatively trivial. All that is a method of determining the reachability of directly attached subnets. That's why we say it's kind of a half a routing protocol. Then there's Routing Information Protocol, or RIP. And RIP is a relatively simple protocol, and it's a distance vector protocol. And what that means is it's based on routers sharing their routing tables with each other. And then there's Open Shortest Path First, or OSPF. And OSPF is the primary and recommended routing protocol for ZOS. And it's a link state protocol. What link state means is that routers learn network topology from each other, and then each one independently calculates its own routing table. All 3 of these protocols are supported by OMPROUTE and ZOS, and they're supported for both IPv4 and IPv6. So on slide 36, connection routing, which is the simplest type of routing. Connection routing basically means when an interface becomes available, OMPROUTE knows its subnet mask, so OMPROUTE assumes a route to that subnet is available. So here we have a host where interface 9.1.1.1/24 comes up. OMPROUTE computes that the subnet is 9.1.1.0 and adds a subnet route to 9.1.1.0 to the routing table with the C flag for connection. So that basically has made everybody in the 9.1.1.0 subnet reachable by a direct route just by putting it out on that interface, because the stack now knows anything in that subnet needs to go out that interface. You'll also notice a second route, which is a route to the interface's IP address. This is called an implicit route. The stack always adds an implicit route for each interface IP address. So one neat little shortcut that I use, because I'm more familiar with routing than I am with devices, I find dev links to be a long display that's hard to read. But if I display the routing table, I can look for all the UH flag routes, and that tells me what interfaces are up on the stack, because those are going to be the IP addresses, the interfaces that are up. So when is connection routing useful if it seems relatively simple? Generally, connection routing is used in conjunction with dynamic routing. So you might use connection routing on one interface and dynamic routing on other interfaces. So if we're attached to a network that uses a flat layer 2 configuration, which means every IP address on that network is in the same subnet, which also means a route to that subnet can reach every host on the back-end network via ARP routing, then connection routing is all you need to reach everybody there. Examples of places where connection routing might make sense is a back-end LAN with one or more blade centers, assuming the blades in the blade center are all single home, don't have VIPAs, or if they do, they're all in the same subnet. The Z Enterprise IEDN is an example of a place where connection routing might be useful. So connection routing is almost never used all by itself. It's usually used in conjunction with RIP or OSPF on other interfaces attached to more complex networks to reach back-end flat networks. All right, slide 38. The next routing protocol that we support is RIP, or Routing Information. And at its most basic level, RIP is based on routers sharing their routing tables with each other. So each router tells its neighbors what destinations it can reach, and routers add their hops and inform their neighbors. So example, on this slide, I have the router on the far left, who's 9.1.1.1.1. He sends a message to his neighbors saying, my IP address is 9.1.1.1. So the second router adds to its routing table that I can reach 9.1.1.1 with a distance of 1. Then it tells its neighbors, look, I'm 9.1.2.2, that's my IP address, and 9.1.1.1 is 1 hop away from me, and 9.1.2.1.2 is 0 hops away from me. So that causes the third host to add his routing table, where he adds the distance, so now he's got a route saying 9.1.1.1 is 2 hops away, and the other 2 IP addresses are 1 hop away. Then he tells his neighbor, I'm 9.1.1.3, that's my IP address, and by the way, 9.1.1.1 is 2 hops away from me, 9.1.1.2 and 9.1.2.2 are each 1 hop away from me, and 9.1.2.3 is 0 hops away from me. So the fourth host adds to his routing table saying 9.1.1.1 is a distance of 3 from himself, the others are 2, and the others are 1. And so on. Now this is a vast simplification. The updates go both ways, so ultimately everybody has routing tables to reach every destination with the distances. Now if you look at this closely, you might think, well, how do you prevent routing loops? Slide 39. the illustration is a simplification of RIP, but it gives you the principles of distance vector algorithms. For example, RIP actually uses subnet routes, not host routes. So you don't have to show the distance to every host route. Now RIP has algorithms to prevent routing loops. Another thing about RIP is the distance value defaults to 1 per hop, but interfaces can be configured to have higher distance values if you have a path you'd prefer. And then another thing about RIP is that the complete routing tables are resent every 30 seconds. So once this stabilizes and every host has a routing table with a bunch of routes, every 30 seconds they resend it to all their neighbors. If you don't hear from a route within 3 minutes, it's considered unreachable. That's called garbage collection. Now if there are topology changes can be sent out sooner. But RIP routes time out if not refreshed within 180 seconds. Now another thing about RIP is the maximum distance allowed is 15. In RIP, distance of 16 means unreachable. So RIP is relatively simple, and there are both IPv4 and IPv6 versions of RIP, but they work essentially the same way. So the pros and cons of RIP on slide 40. RIP is simple. Here's all my routes, you add your routes to them, you forward the table on. It uses less CPU than OSPF because there's no route calculations being done. You're just accepting a routing table from a neighbor, adding your routes, and forwarding it on. Now the cons are that there's limited network size supported. A distance of 16 means infinity, which means you can't reach anybody that's more than 15 hops away from you. And if people have coded distances greater than 1 hop, that makes your network even smaller. Also, RIP can use a lot of network bandwidth because hosts send their entire routing tables every 30 seconds. RIP is also slow to respond to outages because it takes a 180-second timer to invalidate a route. It's one thing if on a host a single interface goes down, the host can immediately send out an update saying a distance to this interface is 16, making it unreachable. But if the host itself goes down, nobody notices for 3 minutes because that's the garbage collection timer. Also, RIP does not support multipath. So RIP can only learn one route to a specific destination, so that limits network flexibility and availability. So the next protocol is OSPF, which stands for Open Shortest Path First. And OSPF is a link state protocol, which means that routers exchange topology information, not routes. And then each host learns the network topology and then computes its own routing table. So this exchange of topology makes OSPF more powerful, but also more complex than RIP, because now you have to manage a bunch of more things. In OSPF, you have to manage who am I exchanging topology with? How much of the topology do I have to know? How do I represent topology, and how do I build a routing table? Now, a full OSPF tutorial would fill a presentation. As a matter of fact, we had one we used to do at Share years ago. It was an hour and 15 minutes just talking about the OSPF architecture. We clearly don't have time for that, but I'm going to cover some basic high-level concepts, enough so that you can intelligently understand about OSPF, about why we use it and some of its basic operating principles. So the first question you have to answer in OSPF is, how do I know who to exchange topology with? So first thing routers have to do in OSPF is learn who's next door. Who are my neighbors? So OSPF has what's called the hello protocol. And the hello protocol is both a probe and a keep alive. And there's an OSPF packet called the hello packet, and every router multicasts that packet to a special multicast address for OSPF routers. So if you're a router and you want to participate in OSPF, you join the OSPF routers multicast group and you start sending hello packets out that multicast group. Everybody else who's joined the multicast group receives those hello packets. That's how they learn you're there. Now, hellos are sent out on a regular interval, which is configurable. The ZOS default is 10 seconds. If I don't hear from a router for another configurable interval called the dead router interval, then I consider that router down. So the default value for dead router interval is 40 seconds, which is 4 hello intervals. So if I'm receiving hellos from a router, then he stops sending me hellos. After 40 seconds, I assume that router is down. So that's how routers learn about each other, learn that they're there. But then you have to manage the topology exchange. So the next concept is the adjacency. And adjacency is how routers keep track of their immediate neighbors and manage their topology exchange. So when routers are fully communicating with each other and exchanging topology, they are considered to be fully adjacent. In our displays, that's neighbor state 128. Routers go through a progression of states to negotiate and manage their adjacencies. Now, it's important to understand that not all physically connected routers become fully adjacent, which I'll discuss in a second. So slide 43 is a basic illustration of the hello protocol and adjacencies. Router 1 and router 2. They both start out by multicasting a hello packet. As soon as you receive a hello packet from another router, you transition your relationship to him to state 4, which is init, which I've heard from you, right? But then you send back a hello packet saying, this is my IP address, and I've heard from you. As soon as you hear from a neighbor that he has received your hello, in other words, you get a hello from him saying, I know that you're one of my neighbors, then we're in state 2-way, which is state 8. That means two-way communications. Each router has now recognized each other. At that point, we are now what we call merely neighbors. We're not adjacent, we're just neighbors. We know each other's there. Then, if we're going to progress, then we have to start exchanging topology. So we start off by exchanging descriptions of our database, saying this is what I have. Each one lists a summary of every element in the database, and that's when you're in exchange start state, which is state 16. And then once you've learned what your neighbor has, then you send what's called a link state request, saying, I don't have these, please send me these. Right? So you've told me all the topology you have. I've looked in my database. Here are some elements that you said you have, I don't have. Send them to me. When the neighboring router sends those, we're in loading state. And finally, when you're fully synced, your databases are fully synced, you're now fully adjacent. Now, usually when you're looking at displays, states 16, 32, and 64 don't last very long, right? Because they're just doing going through them. It's pretty rare to see something in those states. If you see a neighbor that's in those states for a long time, you've probably got a problem. State 8 and State 4 can last a lot longer, and State 128. State 128 and State 8 are the two states that you want to see most of your neighbors in. And we'll talk about which ones you want to see in State 8 and which ones you want to see in State 128 in a minute. So slide 44, if you think about a LAN with a bunch of hosts and routers on it, suppose you have a LAN with, I don't know, 8 or 10, 2 routers and 6 hosts, for example. Fully messed adjacencies would be a large processing burden. You can already see that to maintain adjacency in OSPF, you have to regularly send hello packets, you have to regularly exchange topology, you have to maintain control blocks. So fully messed adjacencies are a big burden. So one of the optimizations that OSPF includes is called the designated router and the backup designated router. And on a LAN, the designated router and the backup designated router become fully adjacent with every other router. If you're not a designated router, you only become fully adjacent with the designated router and the backup designated router. You don't become fully adjacent with everybody else. So non-designated router neighbors, their states stop at two-way. But designated routers, you go all the way to fully adjacent. So what that means is, for topology exchange purposes, the designated router owns the LAN for OSPF purposes. It gathers topology information from all the members of the LAN and advertises them to the rest of the network. And it receives topology information from the rest of the network and distributes that to the other LAN members. Now that's what the designated router does. The backup designated router is like the vice president. He just quietly waits to take over if the designated router fails. And how do you decide who's going to be designated router? Well, that's negotiated through the hello protocol, but there are configurations you can do to influence it. There's a designated router priority, which is a 1-byte integer value. The higher the value, the higher priority you have. In other words, if my designated router priority is 255, your designated router priority is 128, I'm going to become designated router. So administrations have influence here, and we urge you to use them. The designated router and the backup designated router should not be ZOS hosts, if at all available. ZOS is a data host, not a router. It uses routing. It shouldn't route. You want to have real routers. You have Cisco or Juniper or some other kind of router box on a LAN. You want them to become the designated routers whenever possible. Because the designated router and the backup designated routers, you can probably tell, have a higher processing burden than the non-designated router boxes. So slide 45 illustrates this. I've drawn a LAN here with 2 routers. One's the designated router, one's the backup designated router. I've got 3 hosts. The red arrows indicate full adjacencies. So everybody becomes fully adjacent with the designated router and the backup designated router. The blue arrows indicate two-way adjacency, which means you're only doing hello, keep alive. The hosts only become two-way adjacent with each other. Now you might look at this and say, so big deal. I only avoided 3 adjacencies and I've got about 8 or 9 full adjacencies. But as the number of hosts on the network increases, the more efficient this gets. Because if there were 6 blue hosts on this network, there would be a lot more two-way adjacencies than full adjacencies on this network, and you're saving processing on the hosts. So that's all well and good, but networks can get complicated. So you don't want every host to have to learn the whole network topology. Especially you don't want ZOS hosts to deal with the whole network topology because that's taking up processing. So OSPF has another optimization, which is that the OSPF domain can be subdivided into what are called areas. So within an OSPF area, routers exchange and store topology within their specific area. Destinations outside the area are reached using area border routers and summary routes. So I don't learn topology that's outside my area. I have area border routers that connect my area to the other areas that tell me how to reach destinations in other areas. So in OSPF, areas have names, and those names are 32-bit numbers. And they're written in dotted decimal notation for some reason, so they look like IP addresses. Even IPv6 areas are 32-bit numbers written in dotted decimal notation. So for example, area 1 would be written 0.0.0.1. Now there's a special area, which is the backbone area, which is area 0.0.0.0. And the rule for OSPF is all other areas must attach to the backbone. And all routing between areas must go through the backbone. So the backbone area is, as the name implies, the backbone. Two non-backbone areas cannot be directly connected. You must go through the backbone. So OSPF is hierarchical in that manner. You have to use the backbone to route between areas. There's two other types of area that are important in ZOS. There's what are called stub areas, which are not that interesting. And then there's totally stubby areas, which are interesting. These are special types of areas that limit the amount of information hosts within the area have to learn about the rest of the network. Once again, you have a ZOS box. It's a big box. It's an expensive box. And it's for processing your enterprise data. It's not a router. So we want to use as many optimizations as we can to minimize the routing burden on ZOS boxes. Using areas, using somebody else as designated router, and using totally stubby areas, as I'll explain, are ways to optimize it so that to minimize the routing burden on a ZOS box. So slide 47 is an illustration of an area topology. I have the backbone area, area 0.0.0 in the middle, and I have three areas around it, area 2.2.2.2, area 4.4.4.4, and area 1.1.1.1. This is how you lay out an OSPF network. You have the backbone, you have all the areas connected to the backbone. To route between areas, you have to route through the backbone. So to route from router A to router D, you have to go through router B into the backbone, router C, into router D. Now the routers that connect multiple areas are called area border routers. In this picture, routers RB, RC, and RF are area border routers. They maintain topology for both areas they're attached to. So they're more powerful routers. You probably want them to be regular router boxes as well. And they also summarize destinations between areas. So for example, router B tells everybody in area 2 how to get to destinations that are in other areas. Instead of having them calculate topology, it just tells them. The other routers that are not area border routers, for example, RA, RD, RG, RH, RK, they only learn topology of their area, so they have lesson burden. They rely on the area border routers to tell them how to reach destinations in other areas. So slide 48, let me talk a little about totally stubby areas because they're important for us. As a reminder, routers learn destinations from other areas from summary routes advertised by area border routers. So an area border router will send into its area, here's how to reach all the destinations outside the area. If you have a large WAN, that can still be a large number of routes. You may not be computing a lot of topology, but you're still maintaining a lot of routes. But totally stubby areas are special areas that limit the amount of inter-area topology routers have to know. On the previous slide, I just made 4.4.4 a totally stubby area. The way a totally stubby area works is that what the area border does is instead of telling me how to reach everybody in the WAN, it just sends a default route into the area. So in effect, in a totally stubby area, the area border router says, don't worry about the topology outside the area, don't worry about destinations outside the area, you don't need to care, forward all packets to me and I will route them for you. So this greatly reduces the size and complexity of routing tables within a totally stubby area. And for this reason, we highly recommend that you place ZOS hosts and sysplexes within totally stubby areas whenever possible. Now, because of the totally stubby area, the only way you have to get out is a default route. That means that all the area border routers have to actually be able to advertise a default route. In other words, you have to have contiguous area topology outside of the totally stubby area. If you have two area border routers, and most of our customers do because nobody likes a single point of failure, if you have multiple area border routers attaching a totally stubby area to the backbone, all of those routers have to be able to reach all destinations because they're all going to advertise default routes. There's no way to distinguish which router needs to get which route to which destination. However, a good network design should ensure this because you should have redundancy in your network already. So in slide 49, we're going to introduce one more concept. You can see OSPF gets pretty complicated, and we're trying to simplify it. There's the concept of an autonomous system. So autonomous system is the official IETF approved term for a routing domain. And an autonomous system example, an autonomous system is a network that's running one routing protocol and under one administrative control. So for example, a corporation's OSPF network, that's an autonomous system. The same corporation's RIP network is a different autonomous system. Another corporation's OSPF RIP network is yet another autonomous system. And even static routes are an autonomous system. And the reason that's important is because a router that acts as a boundary between autonomous systems is called an Autonomous System Border Router, or ASBR. And the ASBR's job is to manage the import and advertisement of routes between different autonomous systems. For example, importing RIP routes into OSPF and vice versa. Now, a lot of other routers, especially backbone routers, use another routing protocol called BGP, which ZOS does not support, but we certainly attach to routers who support BGP, and they can advertise as ASBRs. They can advertise BGP destinations to us. So, ZOS supports being an ASBR, but we don't really recommend it. The only time you would want to be an ASBR with ZOS is if you have static routes that you want advertised into the OSPF domain. But hopefully your network is designed so that ZOS is on the edges of the network and you don't route through ZOS. Even though we support being an ASBR, if you're not an ASBR, you still have to know what an external route is. So an external route is a route that has been imported into the autonomous system from another autonomous system. For example, if you're an OSPF network and you have a destination that's reached via a static route or a RIP route, that's advertised into OSPF as an AS external destination. So slide 50, now we've got areas and autonomous systems. In the picture here, we have a backbone area with 4 routers in it. Attached to the lower left-hand corner, there is a little RIP autonomous system, and there's a non-backbone area and a totally stubby area. And these arrows show what kind of advertisements are originated, because one of the keys to topology is routers advertising topology. So for example, router 1 is advertising internal OSPF routing information, in other words, information for that area. He's not an area border router, he's not an ASBR, he only advertises internal OSPF information. Router 3, no, sorry, let me do router 2, because we'll start with that. Router 2 is an area border router. So router 2 originates internal routing information into its own areas, and it also originates summary routing information into other areas. So for example, the arrow that says AC from router 2 pointing into the non-backbone area means that the router originates its interfaces and destinations that are within that area, and then C means it summarizes backbone destinations into that area. The AC arrow going in the other direction indicates that router 2 advertises its area 0 destinations into the backbone area, and then it summarizes destinations in the non-backbone area to the backbone area. This is only origination. This is what he sends to his destinations. Now go down the lower right-hand corner and look at the totally stubby area. The totally stubby area, you see that the area border router advertises into the totally stubby area A, which is its own interfaces that are within the totally stubby area, but it has a D instead of a C, which means it simply advertises a default route into the totally stubby area, telling everybody in the totally stubby area, just go to me to reach every destination not in this area. So that's origination. Then slide 51, the next step is flooding. So origination is telling your neighbors about topology. Flooding is forwarding received topology. So routers receive topology information from neighbors and they flood it to other neighbors, and in that manner all the information about the network gets flooded around. So within the backbone, everybody floods internal, external, and summary OSPF information. Within between the non-backbone area and the backbone area, you get external and summary information flooded. And in the totally stubby area, the only thing that gets flooded is the default route. In other words, router 3 doesn't bother telling the totally stubby area about any topology that's outside the area. It just says, here's a default route, got any questions, come to me. All right, the next step, once we've learned topology, is to build routing trees. So once everybody's learned the area topology, they apply an algorithm called the Dijkstra algorithm, which is a tree calculation algorithm that calculates the shortest path to every destination. So the routing tree represents the best way to reach each destination in an area. And an area border router, which attaches to more than one area member, will compute a separate tree for each area. After the area trees are computed, then the best route to reach each destination is added to the routing table, along with external routes, which are from outside OSPF, and summary routes, which are from other areas. And from that, that's how the routing table is built with OSPF. So, like RIP, OSPF, we're on slide 53 now. Like RIP, OSPF computes subnet routes, right, to reduce the number of routes in the routing table. Instead of having to have a host route to everybody, OSPF computes subnet routes. For example, if you have an IPv4 LAN, a subnet route reaches everybody on that LAN, right? Because every interface on the LAN has to be in the same subnet. So there's no need to add host routes for all the host interfaces on a LAN, because they'll all be in the LAN subnet. So once you've routed to somebody on that LAN, you can reach everybody. Now this also applies to VIPAs. VIPAs have subnets as well, but you have to be careful. If there are multiple VIPAs in the same subnet on different hosts, then a VIPA subnet route doesn't help you, right? You have to have a VIPA host route, because routing to the subnet doesn't get you to the VIPA, right? If you have a VIPA if you have 2 VIPAs in the same subnet, they're on different hosts. If all you have is a subnet route, we don't know which host to forward to, unless you're doing flat layer 2, and then you can find it with ARP. But if the VIPAs are in their own subnet, that doesn't work. Now, IPv6 has more flexibility than IPv4. So we've talked a lot about IPv4. With IPv6, there's a lot of flexibility in assigning IP addresses. So unfortunately, that means for IPv6, you generally have a lot more host routes because the rules aren't as hard and fast. There aren't subnet guarantees in IPv6. Another thing about IPv6 is the next hop is always a link local address. Global addresses are never used as next hop destinations in IPv6. So 54, we've talked a lot about OSPF. There's OSPF for IPv4 and OSPF for IPv6. They both work basically the same way, but there are some differences. So in OSPF version 2, which is for IPv4, all routers and links are represented by their IP addresses. And one of the IP addresses on a router is chosen to represent the router, and that's called the router ID. For ZOS, we recommend you use a static VIPA. For IPv6, it's different. Routers and links are represented abstractly, because remember, IPv6 addresses can be auto-configured, there can be multiple addresses, so then they aren't a good way to indicate a host. So all routers and links are represented abstractly. Routers are represented by a router ID, which is also a 32-bit number, represented in IPv4 style notation, but it's actually an arbitrary value. Links are represented by an interface ID, which is an arbitrary 32-bit value, but it's an integer. And then the actual IP addresses are advertised separately from topology and referencing topology. For example, you would get an advertisement in IPv6 saying, hey, you know that link 23 on router 1.1.1, its IP address is 2001:0 dog baker 8::9:7. So to build the routing table in IPv4, you build the tree to find the best route to each IP address. Because IPv4, all IP addresses are global, and each interface and host has one IP address, that's easy. For IPv6, you build a routing table, you build a tree to find the best route to each abstract topology element using the link ID and the router ID. And once that tree is built, then you overlay the IP addresses onto that tree to create the routing table. So, pros and cons to OSPF. OSPF, the pros are significant network design flexibility, right? You can have virtually unlimited network size and complexity. Also, after initial synchronization, topology information is only flooded when it changes, so it uses less network bandwidth than RIP. That's kind of a lie because every 30 minutes, every OSPF topology element has to be refreshed. That's a lot better than sending the whole routing table every 30 seconds. So OSPF uses significantly less network bandwidth. Also, OSPF responds to out-of-distant topology changes quickly because it uses proactive notifications and timers instead of relying on garbage collection like RIP. And OSPF supports multipath, meaning it can compute multiple equal path routes to a single destination. What are the cons of OSPF? Well, you probably figured one out already. It's very complex. So the main drawback of OSPF is its complexity. But OSPF also uses more CPU than RIP because it has a bunch more timers and it does internal route calculations. So, now you're an expert in OSPF, right? We spent 30 minutes talking about it. OSPF is complex and large, and we've only scratched the surface. And I've done a lot of simplification in the interest of time to make this fit an hour and a half. A full OSPF tutorial would be a presentation on its own. And quite frankly, to do ZOS, you don't have to know all the details of OSPF. You have to know enough to attach intelligently to the network and configure OMPROUTE. You're not going to be a backbone router if you're a ZOS box. But if you want more detailed information on OSPF, this slide shows you the links to the RFCs where they're specified in the IETF. And these are the levels that OMPROUTE supports. For example, I point you to RFC 2328, which is an obsolete version of the OSPF RFC, but it's the version we support. There are further enhancements, but we don't support them, so 2328 is our level of support. Same thing with OSPF for IPv6. RFC 2740 is the level of OSPF IPv6 that we support. So now let's get down to the brass tacks of talking about dynamic routing on ZOS. Starting on slide 58, let's talk about OMPROUTE. I mentioned it before. OMPROUTE is a daemon. It's a ZOS Unix daemon that runs in its own address space, and it performs all the dynamic routing functions. OMPROUTE stands for Open Multi-Protocol Router. We named it back when ZOS Unix was called OpenMBS, or OMBS. So anyway, that's what that is. And OMPROUTE implements OSPF and RIP and connection routing for both IPv4 and IPv6. That's a cute typo there on that slide. Both IPv4 and IPv4. And it does connection routing. And the way OMPROUTE works is, if you look at the picture on the right, OMPROUTE gets input from several sources. Down at the bottom, you have the TCP/IP stack. Static routes coded to the TCP/IP stack and the IP interface configuration are learned by OMPROUTE. The stack uses what's called a TCP informational socket, which is an internal Unix socket that OMPROUTE opens to the stack. And the stack sends OMPROUTE messages telling it, these are the static routes that are configured, these are the interfaces that are configured. If there are changes to the static route configuration or the interface configuration, TCP/IP stack sends messages to OMPROUTE on the informational socket. So it learns local topology information from the stack. Then it has its configuration table, and it also communicates with other routers and learns link and route information from the network. Puts those things together, computes a routing table. But that's not the stack routing table. OMPROUTE computes its own routing table. And then once OMPROUTE builds its routing table, it sends ioctl messages to the stack to update its routing table. So OMPROUTE learns local configuration from an informational socket, learns remote configuration from the network, builds a routing table, and then sends ioctls to the stack to update the stack's routing table. The important thing to remember here is OMPROUTE is only responsible for putting routes in the stack's routing table. What the stack does with them is the stack's business. So for example, if Multipath is not working right, it's the stack's fault. Right? The stack uses the routing table that OMPROUTE builds to do the actual routing. So, slide 59, first thing you got to do with OMPROUTE is configure it. It's a ZOS Unix daemon that uses a configuration file, and it uses an environment variable to find its configuration file. So you have the OMPROUTE_file environment variable, which is usually specified in the standard environment file, which is pointed to by the std-env card in the OMPROUTE started proc. Almost everybody starts OMPROUTE with a proc. You can start it from the command line if you want to, for testing maybe, but in production, OMPROUTE is always started from a proc using a standard environment variables file. So here's an example here where you have an OMPROUTE started proc. The std-env card points to a file in the ZOS Unix file system, and that file contains the OMPROUTE file environment variable, so that's how OMPROUTE finds its config file. Yes, it is a little bit roundabout. It's not as convenient as looking at the TCP/IP's profile. You have to open an extra file. We ported a Unix application, so that's how that works. In the OMPROUTE configuration file, you specify general routing information for each routing protocol, and then you specify the dynamic routing characteristics of each of the stack's interfaces. So let's look at some examples. Slide 60. Start off, we're going to configure some OSPF. So we have an OSPF statement. We indicate what's the router ID of the stack. It's got to be an OSPF interface on the stack. We recommend you use a static VIPA. Then you list the areas we're attached to. In this case, we're attached to area 1.1.1.1. It's a stub area, and it's a totally stubby area. Import summaries equals no means it's a totally stubby area. We're also attached to area 0.0.0. Remember, if you're attached to more than one area, one of them has to be the backbone. All right? Also, we're an AS boundary router, so this is a pretty complex router. And we import static routes into OSPF, and we import RIP routes into OSPF. Now, when you import routes into OSPF, external routes are not allowed in stub areas. So this guy will only import into the backbone area because that's the only non-stub area that he's attached to. So since we're an area border router between area 1 and area 0, we will import summaries of area 1 into area 0. In other words, we'll tell area 0 how to reach all destinations in area 1. But since area 1 is a totally stubby area, we're not going to tell area 1 how to reach destinations in area 0. We're just going to send area 1 host a default route, telling them just come to me, don't worry about it, I'll handle it. You wouldn't really do this in OSPF, but this is just you wouldn't really do this in ZOS, right? But this is just an example configuration. You would have a regular router doing this in a real production environment. Next, slide 61, we got to configure some OSPF interfaces. I'll start with a couple of VIPAs, right? VIPAs are OSPF interfaces as well, and VIPAs also attach to areas. That may not be clear, but they are part of an area topology. You have to pick an area for VIPAs to belong to. So you define a VIPA, you tell me the IP address, and you tell the name. They must match the stack's definition. And then you have the subnet mask. You have to tell OMPROUTE what the subnet mask is, and OMPROUTE does not support the slash notation, so you have to code it as a mask. You tell which area it attaches to, and you also, this is how you control whether or not OSPF advertises a host route or subnet route for the VIPA. Remember, if the VIPA subnet only exists on one host, you only have to advertise the VIPA subnet route. But if the VIPA subnet exists on multiple hosts, you have to advertise host routes for the VIPAs. Now the next interface definition is a special wildcard for dynamic VIPAs. OMPROUTE has special treatment for dynamic VIPAs. For dynamic VIPAs, you define it by the subnet number. And what OMPROUTE does is any interface that comes up, any dynamic VIPA interface that comes up that the stack notifies us that falls into that subnet will use this definition. So any VIPAs, any dynamic VIPAs that are in the 10.138.200.160 subnet, when they come up, OMPROUTE will say, okay, this VIPA belongs to area 1.1.1.1. So for IPv4, when you're matching a stack VIPA interface to an OMPROUTE definition, if it's a static VIPA, we match on the IP address and then verify the name matches. If they both don't match, we won't use the definition. If it's a dynamic VIPA, we look for an exact match first, and if we don't find that, we use these special wildcards. Next is an OSA interface, or hypersockets. With an OSA interface, once again, you define OMPROUTE, you give the IP address and the link name. They need to match the stack. You tell OMPROUTE what the subnet mask is. That's how OMPROUTE computes the subnets. You tell him what area he's attached to. You also have to tell OMPROUTE the MTU. Now, I'll admit, this is kind of a pain. If you do not specify the MTU to OMPROUTE, we will use the default value, which is 576. You probably don't want 576. What happens to this MTU value is every route that OMPROUTE computes that goes out this interface will have that MTU assigned to it. So every route that OMPROUTE computes that goes out this interface will use an MTU value of 1500. So if you don't define it, that value will be 576, which is probably too low. Also, I've coded router priority equals 0. That means I will not become a designated router. Hello interval and dead router interval are how we control those timers. And I also specify an OSPF cost. OSPF has a lot more flexibility on cost than RIP. You can go up to 64K. So I'm specifying a cost of 100. The next definition is a hypersockets interface. It also attaches to area 1. Notice the MTU size is 8,000 because hypersockets doesn't quite have the same limitations as physical interfaces. Now, one thing about hypersockets is, I've been saying over and over again, don't let ZOS become a designated router. But in hypersockets, somebody has to, right? Because no routers can attach to a hypersockets network. So in this case, the router priority of 10 means, okay, I'll be a designated router. You also notice I've coded a cost of 50 instead of 100. What that means in OSPF terms is that the hypersockets is twice as desirable as the OSA. Remember, lower cost is better in OSPF, which makes sense, right? Because hypersockets is faster than OSA. Slide 63, wildcard interfaces. I'll just touch on these real quickly to make sure we don't run out of time. You can also, if you have multiple interfaces that have similar IP addresses that are reasonably grouped, you can code multiple of them all together with one wildcard interface. For example, the first definition will define every interface whose IP address starts with 10.72. If you don't have a more exact match, then this interface definition will be used for all interfaces that come up that start with 10.72. You can wildcard 1, 2, 3, or 4 octets. Obviously, just like the stack, we'll try to use the most specific match first. So when the stack tells OMPROUTE about an interface, we'll look for an exact match in our definitions. If we don't find that, we'll start looking at wildcards, starting from most specific to least specific. All right, slide 64. What about IPv6 OSPF? This is one area where IPv6 is simpler and easier to use than IPv4. And we say that's because of the nature of it. But the reality is we coded IPv4 OSPF in the 1990s. We coded IPv6 OSPF in the 2000s. By the time we coded IPv6 OSPF, we learned a few lessons, right? So we did it a little bit better. First of all, remember the router ID in IPv6 is an arbitrary value. It doesn't have to be an interface, but you have to code one. IPv6 areas work just like IPv4 areas. Just like IPv4, the IPv6 backbone is 0.0.0.0. These interfaces definitions look almost exactly the same, except they're IPv6 instead of just plain interfaces. Plain definitions. Then slide 65, IPv6 OSPF interfaces. These are very simple. Because IPv6 addresses are dynamic and they're often auto-configured, you only have to tell me the name, right? So when the stack tells OSPF about an IPv6 interface, it simply looks for a definition with a matching name, and as you can see here, you can use wildcards. So that's much simpler. And then, so for example here, all IPv6 interfaces whose name starts with OSA 6 will be attached to area 616161, have a 0 router priority and a cost of 100. So that's a simpler definition. VIPAs are the same way. Another thing you don't have to define an IPv6 OSPF is MTUs. I just got through saying you're in bad shape if you don't define an MTU to IPv4. Well, for IPv6, we learn the MTU from the stack. So for IPv6, OMPROUTE learns the MTU value for an interface and the IP addresses from the stack, so you don't have to define them. Because we learn so much more from the stack, the definitions are much simpler for IPv6 OSPF than for OSPF. And there's a third class of interface, which is called generic interfaces. These are interfaces over which no routing protocol is being run. And the reason you define them is to tell OMPROUTE the subnet. If you don't tell OMPROUTE the subnet, we'll use the class subnet. So for example, the 10.1.1.14 interface, we would assign, if you don't define it to OMPROUTE, OMPROUTE will define an MTU of 576 and a subnet mask of 255.0.0.0, and could add a route to the routing table directing all 10 network traffic to use this interface and use an MTU of 576, which is probably not intended. So by defining it to OMPROUTE, you prevent that. This would probably be an interface to a network where you're only using static routing. It's relatively rare, but it can happen. All right, now slide 67. Let's talk about RIP definitions. RIP definitions work similar to OSPF. You define a RIP interface, you match the name and IP address for IPv4, and you define the RIP characteristics, which there are a little bit fewer of them. But one of the RIP characteristics, you have to define the MTU just like OSPF, and you define the metric. The metric default value is 1. Now remember, in RIP, a distance of 16 means infinity. So you don't have a lot of flexibility here. If you define the in metric of 10, and then your neighbor has an in metric of 10, you're unreachable because you're greater than 16. So generally, the default value of 1 is used. In the interest of time, we're not going to go over RIP in detail. It's analogous to OSPF in most ways, except you're specifying RIP information instead of OSPF information. So now we'll talk about monitoring OMPROUTE. OMPROUTE has an extensive set of display commands to help you see what's going on. Okay? And you access OMPROUTE's displays through the display TCP/IP command. So it's display TCP/IP, TCP/IP job name, and then the keyword OMPROUTE, and then the OMPROUTE display command. That can get kind of long and be kind of a burden to type, so we gave you a cheap little shortcut. You can also do a modify. You can do all OMPROUTE displays using the OMPROUTE modify command. So if you say modify OMPROUTE job name, you can put an OMPROUTE display command there, which is a lot less typing than typing TCP/IP, TCP/IP job name, OMPROUTE. OMPROUTE has lots of displays, and we'll go over some of them to display internal routing tables, interface information, neighbor information, topology information. So on slide 69, this is OMPROUTE's internal routing table display. Remember, as I said before, OMPROUTE creates its own internal routing table and then uses that as the basis for sending ioctls to the stack to update its routing table. So it looks slightly different. In the OMPROUTE internal routing table, first of all, the type is different. The type is what kind of OMPROUTE route is it. When you go to the routing table to the stack, all you know is OSPF, RIP, or connection. With OSPF, we give more detail. SPF means a route that's within this area. SPIA is an inter-area route, means it was learned from a summary. Direct means it's a connection route. And SPE means that it is an external route imported by an AS boundary router. Also, if the next hop is an interface name instead of an IP address, it indicates a direct route. And also, if you're doing multipath, this route table display doesn't show you all the paths. You look at the last route in the list, it shows you one of the routes and tells you there's 2 more to look at. So you can go to the next slide, and you can do a display of a specific route, and that will show you all the multipaths. So another thing I want you to notice on this slide, I did a display TCP/IP OMPROUTE RT table. The destination is a host route 9.68.101.66. The route that OMPROUTE returned is a subnet route to 9.68.101.0. So there was no host route to this host, but there was a subnet route. That was the most specific route. That's what OMPROUTE uses. We tell you the mask. It's an SPF internal route, which means it's within the area. The distance is 6. It's been 1,344 seconds since this route was recomputed, and there are 2 ways to get there, and these are the next hops. So that's how you look at that. Generally, if you have a routing problem, you don't see a route you want in your netstat routing table, check the OMPROUTE routing table, see what it says. Next, interface information is pretty important in OSPF. So you can do a display TCP/IP, OMPROUTE, OSPF interfaces, and it will give you a list of the interfaces. It'll tell you the state of the interface, and the state values are documented in IP system administrator's commands. It'll tell you how many neighbors and how many adjacencies. If you look at the OSA interface, you can see I have 4 neighbors but 2 adjacencies. I'm not the designated router, but I became adjacent to the designated router and the backup designated router. I didn't become fully adjacent to my other 2 neighbors. So that's why that number can be different. All right, slide 71, you can get more details about an interface. For example, if I do a detailed display of a specific interface here, it'll tell me who I think the designated router and the backup designated router are. So these are my selections for who I think they are. Also, notice on the display the maximum packet size is 556. That's awfully small. So what happened there was somebody forgot to configure the MTU value to OMPROUTE, so OMPROUTE used the default. And that was probably not what was intended. It's probably causing excessive fragmentation. So remember, you need to tell OMPROUTE the MTU value of IPv4 interfaces where it will use a default of 576. And the reason the max packet size is 20 less is because that's making room for the IP headers. All right, now there are similar displays for RIP information, IPv6 information. There's all kinds of displays, but you can tell we're running out of time, so we don't need to go over all of them, but they all work similarly. There's, you might notice though, you substitute, you just add IPv6. So for IPv6, it would be IPv6 RIP and IPv6 OSPF. For IPv4, it's just RIP and OSPF, and then to display interfaces that are not running a routing protocol, it's generic and generic 6. Next thing we can display is the neighbors. Now here's an example where I'm on a single OSA LAN. I have OSA QDIO1. I have 5 neighbors. My state with 2 of them is 128, so I'm fully adjacent to 2 of these neighbors, and I'm only 2-way to 3 of them. So the top 2 neighbors are the designated routers and the backup designated router. I'm fully adjacent to them. I'm only 2-way adjacent to everybody else. Now also notice the neighbor address, that is the IP interface address of the neighbor on the common LAN. The neighbor ID is the neighbor's router ID. They may or may not be the same. If they're ZOS, they're probably not. The neighbor ID is probably a static VIPA on that neighbor, and the neighbor address is that neighbor's OSA address on the LAN. Now neighboring relationships are important because neighbors is how we learn topology. So you'll be looking. So if you have topology problems, another place to look at is the neighbor display. The neighbor display tells you who, like if there's a router missing from here, then we don't know about him. We haven't received his hello packets, for example. Or if there's a router in here, you expect the state to be 128 but not 8. That's also an indication of a problem. You can also do a detailed neighbor display. When you do a detailed neighbor display, it'll tell you which interface we reach him over. So it'll also tell you who the neighbor has chosen as the designated router and the backup designated router. So if I display my interface OSA QDIO1 and my DR choice and backup DR choice are not the same as the neighbor's, something's out of sync. So that's another thing to look for. Next slide. There are more displays. OMPROUTE has a lot of displays for displaying topology database information, which we don't have time to go into here. But you can do a display of an area summary display. You can display the topology database of an area. You can display information about specific topology advertisements. So with all these, there's OSPF versions, and then there's IPv6 OSPF versions of the same displays. So you know, it works pretty much the same for IPv4 and IPv6. And that's the end.